Hello everyone and welcome to Chapter 13. Chapter 13 covers the trace minerals. These are your learning objectives. An overview of trace minerals. So trace minerals, essential mineral nutrients that human body requires in relatively small amounts, less than 100 milligrams per day. Sources include a wide variety of foods, and it will vary with soil and water composition as well as food processing. Deficiencies can affect people of all ages, and they may be difficult to recognize. Because minerals are active in many body systems, including your digestive system, cardiovascular, muscular, skeletal, etc., deficiencies can have wide-reaching effects and can affect all ages. This is a true or false question. Trace minerals in supplements are tightly regulated by the FDA. The answer is B, false. By law, the FDA does not have the authority to limit amounts of trace elements in supplements. Toxicities may occur as a result. So it's up to you, the consumer, to be aware of the possible dangers and choose supplements that do not exceed daily values by much. Interactions are common and coordinated to meet needs. They can lead to nutrient imbalances. Excess of one can cause a deficiency in another. For example, too much manganese can aggravate an iron deficiency or interfere with the work of another mineral. For example, selenium deficiency halts the activation of the iodine-containing thyroid hormone. A good food source of one nutrient may be a poor food source of another. For example, meats tend to be a good source of iron but a poor source of calcium. Factors that enhance the action of some trace minerals may interfere with others. Vitamin C enhances the absorption of iron, but it hinders that of copper. Of note, you want to be wary of supplements because they can easily cause an imbalance. Iron, an essential trace mineral that is needed for the transport of oxygen and the metabolism of energy nutrients. You can find it in two ionic states. You have ferrous ion, which is the reduced state, and ferric iron, which is the oxidized state. Iron is able to switch between both states. Ferrous iron can be oxidized to ferric iron, and ferric iron can be reduced to ferrous iron. Body's iron is mostly found in two proteins, hemoglobin, which is in red blood cells, and myoglobin, which is found in muscle cells. I encourage you to pause this presentation for a moment and try to answer the questions yourself. Iron absorption. Iron balance is maintained primarily through absorption. More iron is absorbed if stores are low. Less iron is absorbed if stores are full. Special proteins help the body absorb iron from food. Ferritin is known as the iron storage protein. It stores iron in the cells of the small intestine. When the body needs iron, ferritin releases some iron to the transport protein transferrin. Transferrin is known as the iron transport protein. If the body doesn't need iron, it's carried out when the intestinal cells are shed and excreted in feces. Intestinal cells are replaced every 3 to 5 days. By holding iron temporarily, these cells control iron absorption, either by delivering it when it's needed or disposing of it when stores are full. Iron absorption process. We eat iron-containing food and absorb the iron. Iron is then stored in the intestinal cells. If we need iron, the intestinal cells release it to transferrin, where it can travel in the blood to the rest of the body. If the body doesn't need iron, we excrete it through intestinal cells in feces. I ask that you pause the presentation momentarily and try to answer these questions yourself before I reveal the answers. Heme versus non-heme iron. Iron occurs in two forms in foods. Heme iron, which is found only in foods derived from the flesh of animals, such as meats, poultry, and fish. Non-heme iron, which is found in both plant-derived and animal-derived foods. MFP factor. So MFP stands for meat, fish, and poultry. So the MFP factor. Heme iron contains a peptide called MFP factor that promotes absorption of non-heme iron from other foods eaten at that meal. So basically, it's promoting absorption. Vitamin C also helps enhance non-heme iron absorption. Overall, heme iron is more easily absorbed. Factors that influence non-heme iron absorption. So you have enhancing factors which help encourage absorption, and that includes MFP factor, vitamin C, acids, and sugars. Inhibiting factors are factors that prevent or block or try to prevent that absorption include phytates, vegetable proteins, calcium, and tannic acid. Heme and non-heme iron in foods. About 40% of the iron in meat, fish, and poultry is bound into heme. The other 60% is non-heme iron. So you can see the flesh of the meat has a mixture of both heme and non-heme iron. Heme accounts for about 10% of the average daily iron intake, but it is well absorbed at about 25%. So there's a high bioavailability. All of the iron in foods derived from plants is non-heme iron. Non-heme iron accounts for the remaining 90%, but it is less well absorbed at about 17%. I ask that you pause the presentation momentarily and try to match these together. Factors that inhibit iron absorption. Phytates, found in foods including legumes, rice, and whole grains. Vegetable proteins in soybeans and nuts. Calcium in milk, and polyphenols found in tea, coffee, and red wine. These factors in combination make it difficult to estimate iron absorption. Iron transport and storage. Transferrin, iron transport protein, delivers iron to bone marrow and other tissues. Ferritin, iron storage protein, stored primarily in the liver. Other storage locations include bone marrow and spleen. While most ferritin is stored in the liver, some ferritin is in the small intestine, where it helps regulate absorption based on how much iron we do or do not need. If stores are full, we'll excrete it through feces, and if we need more iron, it can transfer iron to transferrin. Homosiderin, an iron storage protein primarily made in times of iron overload. When iron concentrations become abnormally high, the liver converts some ferritin into hemosiderin, which is another storage protein. Because it releases iron more slowly than ferritin does, this helps protect the body against damage free iron can cause as a free radical. Iron recycling and balance. Recycling iron. Red blood cells live about 4 months. Spleen and liver cells break down red blood cells for recycling or excretion. So what happens to iron? Liver attaches iron to transferrin, and it travels back to bone marrow to be reused in the making of new red blood cells. Balance. Hepcidin regulates iron balance. Hepcidin limits absorption from the small intestine and controls release from liver, spleen, and bone marrow. It increases with iron overload and decreases in iron deficiency. This slide shows how iron is recycled through the body. Bone marrow incorporates iron in red blood cells. Red blood cells carry oxygen through the body. Liver breaks down red blood cells and sends iron to transferrin where it travels in blood and makes its way back to bone marrow. Some iron is lost through blood and sweat. Assessment of iron deficiency. Iron deficiency is the most common nutrient deficiency worldwide. Deficiency develops in stages. The first stage, iron stores diminish, so serum ferritin. Remember, ferritin is the storage form, so this is what decreases first. In the second stage, you've decrease in transport iron. Iron-carrying protein transferrin increases, which enhances absorption, but the transferrin saturation decreases. Then transport iron decreases. Transferrin, the carrier protein, increases, but the actual amount of iron in them is decreased. So basically, there's more transferrin, but less saturation of the iron in that transferrin. The increased amounts of transferrin enhances iron absorption. The third stage, hemoglobin and hematocrit values decline. The third stage occurs when there is so little iron it limits hemoglobin production. Iron deficiency and iron deficiency anemia are not the same thing. Iron deficiency refers to depleted iron stores. Anemia is the severe depletion of iron stores that results in low hemoglobin concentration. Symptoms include weakness, fatigue, headaches, apathy, pallor, and poor resistance to cold temperatures. Basically, you can be iron deficient without being anemic. Results of iron deficiency. With even slightly lower levels of iron, energy metabolism is impaired. Neurotransmitter synthesis is altered. This reduces physical ability to do work and mental alertness decreases. People may seem apathetic and unmotivated. Pica or pica, that's craving and consumption of non-food substances. And examples include ice, chalk, starch, clay, baby powder, and paper. Because too much iron can be toxic, the body closely regulates levels and absorption normally decreases when iron stores are full. However, iron overload can still occur. Hereditary hemochromatosis. It's a disorder caused by a genetic failure to prevent absorption of unneeded dietary iron that is characterized by iron overload and tissue damage. It's the most common genetic disorder in the US. Signs and symptoms are similar to deficiency: apathy, fatigue, lethargy. You want to check transferrin saturation and serum ferritin. This is important to do because you need to determine whether you're in iron overload or deficiency because symptoms are similar. Characteristics: toxic accumulation and free radical damage can lead to cirrhosis, liver cancer, heart failure, and arthritis. Treatment: you can follow a low iron diet, phlebotomy, where you would remove blood from the body, or chelation therapy, and that's a dose of medication or a chelate forms a complex with iron that promotes excretion. Iron recommendations. Iron poisoning. So large doses can cause GI distress. So think things like nausea, vomiting, diarrhea, constipation. Symptoms of toxicity. Again, GI distress, a rapid heartbeat, weak pulse, shock, and confusion. The UL for adults is 45 milligrams per day. The RDA for men is 8 milligrams per day. For women between the ages of 19 to 50 years old is 18 milligrams per day, and it drops at 51 years of age back down to 8 milligrams per day. Women between 19 and 50 years old need more due to their childbearing age and the loss of iron through the menstrual cycle. Vegetarians need 1.8 times as much iron to make up for the low bioavailability typical of their diets. Select the correct answer. Please pause for a moment to try to answer for yourself. Iron sources. Natural sources include meats, fish, poultry, legumes, and eggs. Enriched sources include flour and grain products. Enriched sources do not provide a lot in and of themselves, but because people tend to eat a lot of these foods, they end up being good sources of iron. Here is a slide for the iron in selected foods. Some of zinc's roles in the body: supports the work of thousands of proteins, stabilizes cell membranes and DNA, immune function, growth and development, synthesis, storage, and release of insulin, blood clotting, thyroid hormone function, behavior and learning performance, normal taste perception, and wound healing. As you can see, zinc helps with a lot of different things within the body. Zinc absorption and transport. So rate varies depending on amount consumed, and this can vary anywhere between 15 and 40%. As zinc intake increases, absorption decreases. As zinc intake decreases, absorption increases. Fiber and phytates can inhibit absorption. Phytates are a compound found in whole grains, legumes, nuts, and seeds. May be used or retained in intestinal cells. So the intestinal cells either use the zinc or store it until the body needs it. Enteropancreatic circulation, the recycling of zinc from pancreas to small intestine. Some zinc from food is absorbed by the small intestine and sent to the pancreas to be incorporated into digestive enzymes that return to the small intestine. Therefore, you end up with 2 doses, one at the meal and one via the pancreatic juice. Zinc losses, primarily lost in feces. Zinc can be reabsorbed in the body or can be excreted in intestinal cells shed through feces. Some other losses include urine, skin, hair, and sweat. Albumin is the main vehicle for zinc transport. Enteropancreatic circulation of zinc. Basically, some of the zinc we consume is absorbed by the small intestine and sent to the pancreas. Once there, the pancreas uses some zinc in creating digestive enzymes. So because some of the absorbed zinc is in your digestive enzymes, when you eat food, your body gets 2 doses of zinc, one from the food you just ate and the other from the digestive enzymes. Zinc deficiency. It's widespread in the developing world, but it's not widespread in developed countries. Middle Eastern diets inhibit zinc absorption, and that's for 2 reasons. 1, diets are typically low in meats, which are rich sources of zinc. And 2, the diet is high in whole grains and legumes, which are high in fiber and phytates, which inhibit zinc absorption. Effects include stunted growth, impaired immune response, and central nervous system damage. Zinc toxicity and sources. The RDA for men is 11 milligrams per day, for women 8 milligrams per day. The UL is 40 milligrams. Symptoms include vomiting, diarrhea, headaches, and exhaustion. It also can interfere with copper metabolism. Sources include protein-rich foods like shellfish, meats, poultry, milk, and cheese. Supplementation. In developing countries, zinc supplementation plays a major role in reducing incidence of disease and death associated with diarrhea and pneumonia. Zinc supplementation also may shorten the duration of common cold. Moving on to iodine. Iodine is an integral part of the thyroid hormone that regulates body temperature, metabolic rate, reproduction and growth, blood cell production, and nerve and muscle function. Iodine deficiency. This can potentially lead to goiter, which is an enlargement of the thyroid gland due to an iodine deficiency. This enlargement of the thyroid gland occurs because it's trying to trap as much iodine as possible. It's the most common preventable mental impairment and brain damage in the world. It affects nearly 1/3 of the world's school-aged children. Cretinism, the extreme and irreversible mental impairment and stunted physical growth caused by a severe iodine deficiency during pregnancy. Toxicity interferes with thyroid function. It also enlarges the thyroid gland. So excessive intake can enlarge the thyroid gland just as deficiency can. The UL is 1100 micrograms per day. The RDA for adults is 150 micrograms per day. Sources include seafood, so the ocean and what's associated with it are our biggest sources. So think things like seafood, kelp, and the salt water. Iodized salt. In the US, the addition of iodine to salt helped eliminate deficiency. Selenium. Selenium can act like a substitute for sulfur because it shares similar chemical characteristics. Roles in the body. Antioxidant and part of enzymes that selectively activate or inactivate the thyroid hormones. Deficiency is known as Keshan disease, and it's a heart disease associated with selenium deficiency, characterized by heart enlargement and insufficiency. Sources of selenium, so it's found in soil, meats, milk, eggs, and Brazil nuts. The RDA for adults is 55 micrograms per day. The average US intake does exceed RDA. The UL for adults is 400 micrograms per day, and effects include loss and brittleness of hair and nails, garlic breath odor, and nervous system abnormalities. Copper. Roles in the body, constituent of enzymes, iron metabolism, defense against oxidative damage, and energy metabolism. Sources include legumes, whole grains, nuts, shellfish, and seeds. Copper deficiency and toxicity. The United States diets provide adequate intake. The RDA for adults is 900 micrograms per day. Deficiency is rare. There is a possible link to cardiovascular disease. In animals, copper deficiency raises blood cholesterol and damages blood vessels, which raises the question whether the same happens in humans. This is not conclusive as of yet. Excessive intakes, food versus supplements. So you're more likely to have excessive intake or toxicity from supplementation rather than oral diet. The UL for adults is 10,000 micrograms per day or 10 milligrams. Rare genetic disorders affecting copper status. So we'll talk about two of them. First being Menkes disease. That is when the intestinal cells absorb copper but cannot release it into circulation. Treatment for Menkes disease is to give copper intravenously. Wilson's disease, copper accumulates in the liver and brain, creating toxicity. Treatment includes decreasing your intake or chelating agents to interfere with absorption. Manganese, tiny amounts found in bones and metabolically active organs like your liver, kidneys, and pancreas. Tiny amounts meaning a mere 20 milligrams. Roles in the body. Cofactor for enzymes that facilitate metabolism, bone formation, conversion of pyruvate to a TCA cycle compound, and maintaining healthy nerve cells. Manganese deficiency. Requirements are low and deficiencies are rare. Phytates and high intakes of iron and calcium limit manganese absorption. UL for adults is 11 milligrams per day. They have adequate intake recommendations for men at 2.3 milligrams per day and for women 1.8 milligrams per day. Sources include grain products. Grains are the biggest source, but also nuts, leafy greens, and tea also provide manganese. Fluoride, found in bones and teeth. Deficiency of fluoride can lead to dental caries, basically cavities of the teeth without adequate fluoride. Toxicity leads to fluorosis. Fluorosis is when there is too much fluoride and it causes pitting and discoloration of teeth. You can see that down in the bottom right corner. That is what that looks like. Sources include drinking water. So drinking water is usually the best source, and about 75% of the US community water systems receive fluoridated water. Fish and most tea contain appreciable amounts of fluoride as well. The RDA for men is 4 milligrams per day, and for women, 3 milligrams per day. Chromium, roles in the body, participates in carbohydrate and lipid metabolism, helps maintain glucose homeostasis. Chromium enhances activity of insulin, so when chromium is lacking, you might see higher blood sugars or impaired insulin and glucagon response. There's a diabetes-like condition may result if chromium is lacking. Sources include unrefined foods, liver, brewer's yeast, whole grains. Adequate intakes for men is 35 micrograms per day, for women 25 micrograms per day. Closing thoughts on the nutrients. Look at nutrients as a whole. They work cooperatively with one another. Actions are most often interactions, and most foods deliver multiple nutrients. Basically, we looked at nutrients in great detail, but remember that we eat foods, not just nutrients. So try to look at the overall picture, so meal choices over time, not just one specific nutrient intake. And that concludes Chapter 13.